So as we all know that the material property not only depend on the constitutive material phase, but also it depends on the material geometries in the microscopic scale. So the researcher will try to design the material microstructure such as the geometry of the unit cell to achieve some extreme material properties. Also, people are designing the material structure such as to achieve some global performance, such as to satisfy some displacement deformation. But how to account for fracture resistance in design of heterogeneous metamaterial remains a challenge. Fracture is important. It can often cause some damage on mechanical equipment, and also it can also cause some serious disaster in aerospace and automobile industries. But fracture is a complex behavior which often involves some multi-scale performance in different scales. And also on the other hand, the stress concentration will often cause some premature crack initiation, such as here the crack will be first initiated at the strength concentration phase and penetrating the whole structure like the experiment observed. So in our study, we will try to combine both the structural topology optimization method and also data-driven techniques. So topology optimization is a well-known method right now to tailor the material structure geometries to achieve some best performance, such as here, it's a very classical compliance or stiffness maximization problem. You can try to minimize the strategy of compliance and subject to some volume constraint. Here you have the solid materials and the fluid materials and some physical equations and also the design variable constraint. So here is a very also common structure in topology optimization field is to try to design the air-shaped beam to maximize the strain energy here because we have a displacement loading, and the other part is the same as I described before in the previous slides. So here without any stress control, okay? So you will get a topology like this, and it will have a higher strength concentration around this corner. And if you use the linear elastic fracture mechanics to analyze this brittle material or brittle structure, you will observe that the crack will be initiated at this place where the stress is highly concentrated. However, in other case, if you add a stress constraint, like we did this, and you set a different threshold, and you can find that the optimal structure geometry is totally changed. This rectangular point angle is removed. There's no stress concentration here, and the obtained stress, the maximum value is very close to the threshold we set previously. By doing this, we can analyze the stress effect on the final fracture performance. Here is another look of the strength distribution that we use the same range of the color bar. You can have another perspective to look at the strength distribution of different optimized geometries. And again, if we use the fracture mechanics to analyze the fracture performance of this different optimized structure, you can see that firstly, the crack initiation is changed because the strength distribution changed, the geometry changed, and they are still mainly fractured at this right bar of these two vertical bars. And if you look at the detail of the force displacement curves of all these 6 designs, it's very interesting to observe that the stiffness optimization result, this black curve, will always have this best stiffness. So if you compare with the stiffness result with other design, and if you can obtain a stiffness better than the stiffness-only maximization structure, you'll possibly get a wrong result because, or maybe you get a design to compare with is not a real stiffness maximization result. So here you can see firstly the curve, the slope of the curve of the stiffness-only topology optimization result will give you the highest stiffness. But if you look at the peak node of different curves, you can say that with considering the strength constraint, you can obtain almost 1.5 amplifications compared with stiffness-only optimization results. And if you look at the total area of all the curves, which I measure it as the toughness here, it can achieve more than 3.5 amplifications compared with the stiffness-only results. This is a really significant observation in my mind, and also you can compare also the failure displacements. So with the decrease of the stress threshold or the maximal stress, you can see that the failure displacement is always improved. So right now we only focus on one scale problem. So we have the idea to extend it to multi-scale structures. So we want to tailor the stress distribution or the fracture performance by tailoring the material microstructure. So here is a very simple microscopic structure, cantilever beam, and you have the finite element mesh, which here is a pseudo mesh. So in each finite element, in each location, you will have a different unit cell. So in each unit cell, you will have the effective material property or the stiffness tensor here, and this property will be plugged in the finite element mesh. So by doing this, we built the optimization problem such that we want to find the distribution of the stiffness tensor in each finite element, such as to achieve some performance. Here is we want the maximal stress value of the global structure, which also the homogeneous stress, is very close to the threshold or the target stress value we want. And both of these two values are discrete data, so it cannot be differentiable. So we use a classical p-norm aggregation function to aggregate the maximum stress. And by doing the gradient-based analysis, sensitivity analysis, we can get the fully sensitivity. Here, I do not give the full detail and just give the final description. So with this sensitivity analysis and the objective function, we do the topology optimization of this stiffness tensor component distribution. Here is just the initial design. You have a random distribution of the stiffness tensor, and you can obtain a maximum value of the stress is 1.08. And by doing optimization, we first set a target value of the maximum stress, and you can see our final stiffness tensor distribution is totally changed. And you can see the maximum value of the stress is very close to the threshold we set it already. And of course, you can change the target or the threshold value, and you can always find the optimal distribution of the stiffness tensor, such as finally the homogeneous stress distribution at the global scale, which satisfies this threshold value you already set. This is another design they are also very close to, but this target value is not always can be given in specific design problem. So we use a very general case that we just want to minimize this maximum stress value. And this is the final result. Again, the stiffness tensor distribution is changed, such as the stress distribution is of course changed, and also it's smaller than the previous case. And right now we have this stiffness distribution. And if we want to validate the fracture resistance performance, so we need to assemble the final structure based on each finite element location, and therefore we have a real dimension of each unit cell or each microstructure at each location of the finite element. So we have to find the unit cell and also assemble the structure. This is the place the data-driven the database works. So for each geometry of unit cell like this, the simple structure with the hole, you have the isotropic Young's modulus and Poisson ratio, and you will do 3 different case strain loading, such as you can obtain the effective material properties based on the numerical homogenization method. And we produce different geometries and compute previously of the effective stiffness tensor. We use a lot more than 116,000 geometries. and it will cover the major part of the possible solutions, and also the volume fraction is also covering between like 0.2 and 100%. So it have a large database of the unit cell geometries and the material properties at the same time. And one thing we know that here is that we consider only the orthotropical structure, so it's symmetric in different directions. But extending to ahistotropical geometries is very straightforward. Right now, we have the optimization problem, and we get the stiffness tensor optimized distribution, and we have also the constructed database. So we want to find the best unit cell in each finite element location. But one thing in the material design that different geometries can process the same stiffness tensor values. So another perspective we want to take care of is that when we assemble the final structure, we want the connectivity between the neighborhood unit cells should be connected well. So we use another graph-based optimization method, such as to make sure that the connectivity between different unit cells in the neighborhood is well connected. But by combining all these techniques, we can finally assemble the structure look like this, and you will see that the connectivity between different unit cells is very well. And another thing we want to note is that, as you can observe, the stress here is not a high value, but when you assemble the final structure, the volume fraction at this place is kind of larger than another place. This is because we find that the unit cell geometry is not based on the stress distribution, but we're based on the stiffness tensor distribution. At this place, you can see it's a high value, which will be giving a higher volume fraction at this place. So right now we can obtain the best stress distribution, which has the minimum value, and we can assemble the final structure, and we can do some case studies. Here we first maximize the stiffness of the global structure, and we make it as a periodic structure. For this boundary condition, you will get a periodic structure of the unit cell looks like this. And we can also do some aperiodic structure with the fixed class. Here you have 6 classes, and in each location the volume fraction is changed and the class of the unit cell is changed, so we call it aperiodic structure. And also you can design this structure by our proposed method. Here you can find a free-form structure. The class is not fixed, and also the morphology is not fixed as well, and the connectivity is very well. And for this structure, the homogeneous stress is also well distributed, so there's no significant stress concentration, as we can conclude that that could be a very good design. So by doing the fracture analysis, you can say that the all fracture will be initiated at the displacement, that the place where the displacement is prescribed. And if you look, we name this different structure as lattice structure, GP structure, and N structure, okay? So if you look at the detail of the force displacement curves with the continuous displacement loading here, you can see that the slope, which is the stiffness, is the aperiodic structure of GP with the highest stiffness. Also, the periodic structure for stiffness optimization will have the second higher stiffness, but our design stiffness is still reduced. But if you look at the total energy observed during the whole loading, you can see almost 3 times amplifications compared with both the periodic structure and with the aperiodic structure with the fixed class. And also, the failure displacement is largely improved at 2.5 times better. Here we have another case, which is the pure shear loading, and we first also consider the 2 classical periodic structure, which is plus shape and cross shape. And this is the design we get for the shear test. And also the homogeneity, the stress in the global scale, you can see that the stress, maximum stress is below than the other 2 structure. and the stress is very well distributed. And we also do the fractal mechanics simulation. And this displacement, the periodic structure A is already damaged, but this is not the case for the periodic B and also optimized design we get. And if we keep loading, and the periodic B will also damaged at this displacement, almost 3.28, and the structure we designed based on our framework is have the largest failure displacement. And also the location of the fracture initiation is changed because of the methodology of the global structure is changed. And again, if you look at the detail of the force displacement curves, we know here this is a very brittle structure. So you can observe that the brittle behavior of the force displacement curves. So again, stiffness will be decreased, but the total energy absorbed during the displacement loading is again larger than 2 times amplifications, and also the best failure displacement. Another thing we want to analyze is the size effect. So the dimension of the global structure is the same, but we have more number of the unit cell in the macrostructure. So here is 10 by 20 rather than 5 by 10, and also the geometry is changed here. And the homogeneous stress, we can see it again that it's much better than the other classical structure A and B, and also the fracture simulation give us that the damage displacement and also the fracture location is totally changed. Again, the displacement curve, force displacement curve, we explain everything. So again, we conclude that the amplifications with the smaller size or the larger number of unit cells for same global structure is again can achieved 2 times better, and also the failure displacement is enlarged. If we gather the two cases, the 5 by 10 and 120 of the structure, and we can say that the optimized design will have a large improvement of the structure with the smaller size compared with the large size of the unit cell. Just because we use the homogenization firstly. So with the smaller size, you have the better improvement you will get. But also the smaller size will cause some manufacturability issues. So you have kind of have a balance here. And the other thing is the mesh. So because the total the geometry, the size is changed, so the mesh when you do the fracture simulation is changed. But we analyze the mesh for giving structure and use the coarse mesh and the fine mesh. We totally observe that there's no mesh dependency. Finally, another size effect is the global structure. Okay, so we have the number of the unit cell is fixed, but we change the size of the global structure. As you can see, with the size of the global structure increased, we based on the nominal stress and the strain based on the equation given in this book. And you can observe that the structure material become weaker with the larger size of the global structure. And this phenomena is agrees with the experimental observation in this book. So I come to the conclusion part. So by tailoring the stress distribution and also combine the topology optimization and data-driven techniques, we can tailoring the fracture performance of brittle structure materials. And also the conflicts between strength and toughness of brittle material overcome, as you can see, that our optimized result can achieve a very large amplification of toughness, but also the peak node is not satisfied too much. And also the minimization of the stress will postpone the crack initiation and therefore tough the brittle materials. And also through the optimization global structure with the smaller size of the microstructure, we have better fracture resistance because of the greater design freedom and also the homogenized size effect, which assumes that scale separation. And also with the large size of the global structure, the material will be weaker. So thank you very much for your attention.